All right, next talk is by Peter Plavchan, who's going to tell us about Landau.
Testing, 1, 2, 3. Can you hear me in the back okay? All right, my wife is a huge Eagles fan, so there's some kind of thing going on here. She might be watching too. I'm going to talk to you about the NASA Landau mission. You heard just earlier in this session from Nicole about the Pandora mission. We are the 6th selection of the Pioneers class of NASA astrophysics missions, and we are named after Arlo Landau, who recently passed away, and is famous for, of course, the Landau standard stars. So I'm speaking on behalf of a pretty large team and a large number of students that have already been involved. One of the goals of the Pioneers program is early career development. It's kind of a funny story, but I'll get to that in a minute. But let's talk about the motivation for the Landau mission. One way to think about it is this headline when Webb first launched, which was a bit of a panic. Revised calibrations for Webb are bedeviling researchers studying distant universe. All these very high Z redshift galaxies were coming up, and so we had to start thinking about some of the fundamentals of flux measurement again. And so we have to talk about the difference between precision and accuracy. Most of you already know this, but we sometimes use these words interchangeably. We are currently in this, I gotta figure out how this works. We're currently in this phase right now. We can make very precise measurements, but not necessarily accurate. I can point at a star in the sky and say it's changing by 10 parts per million. But if I then point at that same star in the sky and say how many photons per second are coming from it, I can give you that answer perhaps 2 to 3% in visible near-infrared wavelengths, and then it gets worse from there in other parts of the electromagnetic spectrum. So as I said, we have been selected to try and address that knowledge gap. There's been amazing science that's come out of relative photometry. As we improve our absolute accuracy, we're hoping some additional gains will be coming soon as well. The Pioneers program is a little bit interesting. You propose as a bunch of people that haven't done this before. They give you a budget that's like 10 times smaller than most other missions, and you say, good luck. And do it all in 5 years. So it's a really ambitious program, training early career scientists, going after really kind of ingenious and novel approaches. And one of the things that's novel about the Landau mission is we're a hybrid mission. In order to save money, we're not putting a telescope in space. We're just putting some calibrated light sources in space and pointing them at existing ground-based telescopes to derive our flux calibration. In other words, we will see the star next to the spacecraft, and we turn an absolute measurement problem into a relative measurement problem, since we'll know exactly how much light the lasers on board the spacecraft will be putting out. It'll technically be a small sat, and our baseline requirement is an absolute flux measurement across the wavelengths we'll be operating at of less than 0.5%. So Dan Huber showed this chart at the beginning of the week, and he was talking about the fundamental stellar properties and how important they are. If you zoom in on that little stick, you have stellar properties, and now you have this absolute flux calibration measurement. So maybe the next conference can be named Know Thy Flux, Know Thy Star, Know Thy Planet. Oh, yeah, maybe. But it's an interesting thing. We have not changed fundamentally how we make this measurement of the brightnesses of things we look at for half a century. We use Vega and 3 white dwarf stars in the sky with the CalSpec system, which are all model-based for the white dwarf stars, and then some rocket launches in the 70s and 80s for Vega, and we've extrapolated from there and daisy-chained our calibration measurements since then. Of course, our models have gotten better, our measurements have gotten more precise, but fundamentally what we're doing is replacing those stellar models with NIST traceable light sources that we know exactly how much light they're putting out. So we have 3 main science programs. One that most people here don't care about, but I at least want to touch upon, is supernova cosmology. It turns out, just like we have problems with measuring fundamental parameters of stars, cosmologists are trying to measure the distances to type 1a supernova. So they take a spectrum of a galaxy that has a type 1a supernova going off, and then from the brightness of the supernova, they get a distance, and then they put it on this redshift distance curve, and from that, they infer parameters of our lambda CDM universe, essentially the amount of dark energy in our universe. And so for a perfect lambda CDM model, we'd be up here. And so recent data is starting to show that perhaps there is another tension, not the same thing as a Hubble tension, but potentially showing evidence for deviations from the lambda CDM model of our universe. And it turns out one of the dominant sources today in the sizes of these error ellipses is the flux 0-point absolute systematic uncertainties. We also have exoplanet science cases, which we've heard about all week. So you've seen, of course, the radius valley. And I think it would be nice for some of us to have much more precise radii here in exploring some of the physics and effects going on here, as well as elsewhere in exoplanet science. And our stellar science case is something that Jamie Tyre talked about on Monday. But just in case you weren't here on Monday, it turns out the absolute flux of what we are looking at today, which depending on who you ask, some people say it's 1%, some people say it's 4%, so we just plugged in 2.5 here. It does propagate out to different properties, including planet mass and planet radius. But by improving this number 5-fold, we get the similar number for absolute flux, which then helps us constrain luminosity, then stellar radius, etc. Same thing with temperature by looking at the ratios of absolute color brightnesses. And then that lets you put a good constraint on mass. And then the things get really interesting here. Plato hopefully is paying attention. Right? If you combine these precise measurements of stellar radii and mass, you can actually break some of the degeneracies in looking at stellar ages on the main sequence. So perhaps put some of this stuff into context that we just heard in the prior talk. We're hoping to go to GEO, so it's easy to watch. You basically just point your telescope at a certain altitude and azimuth and turn sidereal tracking off, which is every observational astronomer is not used to doing. They were set maybe for sky fields or flat fields, and we could see the stars streak by. That's one of the observing modes we're going to explore, and we're going to launch somewhere over North and South America. And basically, we're going to pass by, over the course of our one-year primary mission, a bunch of exoplanet host stars and a bunch of candidate standard stars, which we can look at their variability from tests, and develop a new suite of standard stars and highly characterized exoplanet host stars across the sky, and then daisy chain those measurements to the rest of the sky. We'll be looking at Landalt with a set of 4 ground-based telescopes currently. The 2.2 meter SNIFS is going to be one of our primary observatories. It was basically built for supernova cosmology. It's an integral field spectrometer, so it resolves things as a function of wavelength. We're using Palomar with its near-infrared camera, and Rubin will be looking at us too, whether they like it or not, because there's such a big field of view. But we are actually working with Rubin, and we're going to coordinate for Rubin to look at us and help calibrate their system as well. And then finally, my own campus's telescope is actually a really nice telescope. We've done a lot of test follow-up with it. So as I mentioned, we have several different observing modes that we're currently exploring. The one I just talked about earlier was we returned sidereal tracking off. You watch the satellite and the stars streak by. And then there's what you might think the standard approach, where you keep sidereal tracking on and you watch the satellite streak by. One of the problems with this, of course, is that the point spread functions are different. So we came up with a new mode where you track halfway in between. So the stars and satellites streak the same amount, so they have identical PSFs, and thus the aperture corrections cancel out, making this flux calibration problem just a little bit easier. There's still a lot of problems. And we've demonstrated already these 3 different observing modes on a number of our ground stations, and this is just some data from our 0.8 meter. Once we have this data, you might ask what the path to science is. How do we get back to, say, Janskis or ergs per square second per centimeter per hertz, or whatever your favorite flux unit is. We'll have onboard lasers. We'll know how much they're putting out, so we'll see them with the ground-based telescopes. We'll see how much they're putting out because we'll have onboard photodiodes monitoring the power coming out. And then these photodiodes before launch will be characterized via NIST standard reference detectors, which can make absolute brightness measurements to 0.3%. So we'll do this in the lab, and we can actually do this in the far field. So these are not collimated lasers, but they have this nice long tunnel that's dark that we can get into the far field with these lasers. And then these detectors are calibrated off something called POWER, the primary optical watt radiometer. And so if you've never heard of what this is where our SI units are defined for the US. Every country usually has something like the equivalent of this, and every so often they get together and compare their measurements. And so basically you shine a light source into it, the cavity heats up, and you measure that temperature change very accurately. And then from that temperature change, you can infer the energy deposition and thus the amount of light coming out. So we're much earlier on than Pandora. We were just selected last year. We are currently in phase A and very busy over the next 2 months delivering our concept study report, which we hope to have done by March 31st. This summer, we'll have our system requirements review and mission design review jointly. It's like a day-long grilling session. And if we successfully pass this gate, we will enter phase B, phase C, phase D, with a launch hopefully in no earlier than Q4 of FY28. So I will stop there and take any questions.
All right, other questions for Peter about Landau? There's 2 questions.
And I know it's the third to last talk on a very long week, so thanks for sticking around.
Hi, this looks really cool. I noticed that all your ground-based observatories are currently limited in longitude. Are you hoping to extend that, and if so, is that possible?
So it depends on the orbit we end up in, and as part of our initial trade studies, we are looking at different orbits. In fact, we were just messaging about some of the code glitches we had in doing that this morning. But we are notionally planning on a geosynchronous orbit because it's easier to get there via rideshare. We're not going to have our own launch vehicle. We're going to have to hitch a ride, which usually means a military vehicle that's going to that location. So we have relatively limited launch opportunities to put us in different orbits. However, we will have propulsion, and if we do go to a slightly non-synchronous orbit, we'll drift. And it doesn't take many hundreds of kilometers before you start drifting around the entire Earth about once a month. So there is the possibility after the primary mission we could explore moving to over different longitudes.
Travis, did you have a question?
Sorry, this may be a naive question too, but you know exactly how much power is coming out of the laser, but don't you need to know exactly the distance to the spacecraft as well?
Yes, you absolutely need positional awareness, right? So we're going to have a requirement on that of 0.1% knowledge, and for 36,000 kilometers, that really is positional knowledge to 36 kilometers, and there's a few options we have that can do that. It's not terrible. We don't need to know it to the nearest centimeter, which would be challenging.
Are there other questions for Peter? All right.
Yeah, thanks. So how bright is this thing compared to a star in
Yeah,
magnitude?
so I'm sure there's going to be conspiracy theories about space lasers when we get this thing going, but it will not be visible to the unaided eye, and it depends on the final laser powers we end up with, but they're on the order of 100 to 200 milliwatts. So once it gets to the ground, we're looking around 15th magnitude, so definitely not that bright.
The only thing I would add to that, Tim, is that that's part of the challenge of the observing, right, is that the satellite and the stars are not the same brightness. Yeah. Are there other questions? Yeah, way up there.
Thanks, David.
This might also be a naive question, but at 15th magnitude, do you have to deal with any problems of the satellite's own reflectance? And how do you deal with that?
Yes, we have looked at that. And fortunately for us, there is a clone of our satellite bus already in GEO, flown by the Air Force Research Lab. So we have data on exactly how much solar light it is reflecting. And we are considering the addition of a tech demo at this point that will intentionally reflect sunlight with an area and a surface that is well calibrated. Fortunately for us, we get umbral crossings. And depending on the inclination we end up with, but just straight over the equator, you get about 12 weeks of the year where you pass through the Earth's shadow at the equinoxes for an hour per night, and our lasers can only operate for around an hour per night. So we can, quote unquote, turn off the solar reflections if we need to.
All right, with that, let's thank Peter.